How you guys doing today? Doing good? Perfect. All right. So once again, I mentioned this on Monday lecture. If you watch the YouTube channel video, you already saw this, probably some of you. But you know, if you did well on the exam one, that's good. Even though you didn't well on the exam one, we still have a lot of room. You guys know why, right? Exam policy. So you can drop the one lower midterm grade will be replaced by your percent score of the final exam. So you're not missing anything yet, but if you did well on the exam one, means it's really good for, doing exam two without a lot of stress because you're doing exam one. Okay? So make sure you guys do just at least one of the midterm exam, but also do one in the final revisions. Okay? And also we have extra credit as well, everyone, Wednesday and Friday. So eventually you get a lot of chance to run the course, which already happened in so many previous semesters already. So, all right, so the last time we talked about the organic reactions. So we talked about the additions, substitution, eliminations, and rearrangement reactions, and so forth. It's just simply how you're gonna use your reactions to make what type of products. It depends on those type of reactions. And also we talked about the radical reaction and the polar reaction. So we haven't got to much of the polar reaction yet, but for radical reaction, we saw the homocleavage breakage of the bond, so that gives some radicals formation when they break the bonds in half and half, just one for each. But the polar reaction, because of the electronegativity or polarizability that we talked on Monday, they may do actually show the full or pair of electron move at the same time. So the difference between these two is mainly just this one is the one you need to use fishing hook that will show you some the movement of the one electron. But when the polar reaction, you're going to use full heavy arrow, just showing a pair of electrons, two electrons, moving at the same time. So today we're going to focus on the polar reaction. Last time we focused on the radical reactions, but let's do polar reaction today. Okay? Like I mentioned on Monday. Okay? So polar reactions, as I mentioned, there's a couple of things you should know. There's a nucleophile once again. This one's a bit of review again. And the electrophile. So nucleophile simply means something that like to chase something that is the positive, because the nucleus simply means a nucleus. Okay? So if you have something that you're chasing for the nucleus, which is made of the protons and neutrons. Okay? So mainly you can say it's a positively charged something. Okay? So nucleophile is the one that chase something that is positive, or you can say nucleus is the same thing, and that is opposite, right? That likes to bond it to something that is negative, because it's chasing something that is electron simply means it's electron, most likely electron. Okay? Or something that is negative. So if there is some reason where you can find a lot of electron, or you can say electron-rich elements, this is the one that kind of following that elements or the electrons. Okay. So those are the one I want you to remember here. So we're going to use this a lot today. Okay? So nucleophile that follows the chase to something that is positive. The electrophile is that something that chase to something that is negative. Okay, makes sense, right? So far so good. Because it says in the name already, so it won't be very confusing. Okay. So we can denote this in the NU or E. Sometimes I do this, so keep this in your mind too. And then one more thing I want you to remember from the Monday lecture before we move on is if that is chasing something that is positive, most likely, not 100%, this is going to be negative charge, right? So if it has some element with a very high in electron density, there will something that is very electron poor element. That's kind of a natural phenomenon we can see by following the Coulomb's law. So a nucleophile for maybe 90% or 95% chance it will be negative charge. That's why it's chasing something that's positive. So this one will be most likely, not always, but most likely, very high chance it will be something that is positive will become your electrophile. So that's why it's chasing something that is negative. Okay, makes sense, right? It's just kind of all this plus and minus thing we're gonna do today. So if I give you, let me guess if I give you this one, can you guys guess it's electrophile or nucleophile? Perfect. So this will be and then let me give you this one. Okay. This will become, so if I give you this elements in the exam, then you need to choose if it's nucleophile or electrophile. This will be nucleophile. Okay, so this is quite easy, right? So you need to look for something that is positive or negative. You can say electrophile or nucleophile. This is a kind of common job you need to do on the exam. But I'm doing this because there might be a bit of a tricky question like this. This is a methylamine. So it's a methyl groups and amine groups. It's a methylamine. Can you guys guess if this is a electrophile or nucleophile? I'll give you the structure. Here, okay? So what do you guys think? Do you think it's electrophile or nucleophile? Just let me tell you, it's a tricky one. So, but I just want to think about, do you think it's electrophile or nucleophile? Nucleophile. Nucleophile, right? Okay. Because of this. Okay, so that is very good answer. I'm very happy because this one will have a lone pair. They can actually chasing something that is positive. Absolutely correct. But this is kind of tricky because because this hydrogen over here. So those might be okay. Because if you think about the electronegativity wise on the carbons and hydrogen, it won't be so different much, right? So we almost consider those two bonds as like a non-covalent, non-polar covalent bond. You guys remember this? Polar covalent bond, non-polar covalent. So it all depends on the electronegativity between these two elements in the bonds. Okay. So this is quite okay now. Okay. But for those ones, say the nitrogen to the hydrogen. And if you look at the periodic table, the nitrogen is quite, on the top right corner of the periodic table, which means what? It's a highly electronegative, right? So in that case, the gap between electronegativity between hydrogen and nitrogen will be quite large. Makes sense, right? So what happened to this one is this element in here from those bonds, but as you know, the bond is just simply what? The common area, they share the covalent electrons, okay, together. So there's two electrons here for sure, I know, but it tends to close to this one than here because the electronegativity is much higher in here because it has a more strong power to pull electron to themselves. Makes sense, right? Because the nitrogen is highly electronegative. Okay, does it make sense? So think about this one. So this region here, those two, especially those hydrogen bound to the nitrogen, will be electron poor because of this. Okay, so those two might be a target from other the nucleophile too. Okay, so then this will behave like electrophile because of this one. So I know it's tricky, but the correct answer for this one is they can behave like electrophile, nucleophile, depending on the circumstance. So if they have a much stronger nucleophile than this one, they'll behave like electrophile because of this hydrogen. So it's more like a relative term we're going to use. So obviously, I don't think I'm gonna put this on the exam. I'm just gonna put the compounds with the negative charge or plus charge, or very, obviously nucleophile, electrophile, right? But this one, I just telling you because sometimes you may see this on the later chapters. That's why. But it won't be on the exam like asking if it's electrophile or nucleophile. You can say it's both, but it's too tricky, right? So, but it kind of makes sense because of the hydrogen and nitrogen. They can be nucleophile or electrophile because of this. Okay, so can I move on? All right, so I think we're pretty good with the nucleophile and electrophile. So, okay. So this is also a bit tricky, but I promise you, I'll give you some problems. We'll have some time to do it together, so don't worry about it. But just at least hear me once, so you can have some good idea how we can solve the problem in the first place. So if you have some alkene compounds like this, sometimes you need to think about the double bonds in the compounds, and then it's actually made of the one pi bond and the sigma bond between these two carbons here. You guys remember this, right? That's why it makes the sp2, sp2, and then one pi electrons and the p orbital will make pi. Okay? So in here, it's one pi sigma, which is sp2. Okay? So meaning, so technically it means that they have a pair of electrons here on the p orbital, which is on the bit of a away from your sigma bond, and the center from these two centers from these two carbons over here. So whenever you think about this one, the electrons in the p orbital, we can say pi bonds, pi electrons, are able to attack something that is positive. Okay, that is very common in the organic chemistry. So guys, remember this one, please. You guys taking over too? Maybe you'll see this very often. So just remember, there's a double bond because of the electron, the p orbital is quite away from the two centers of the carbon. They're more available than one in the between. So this is more strongly held by these two atoms, nucleus, which is a carbon nuclei, and then there's the electrons in the p orbital is a bit away from here. It's just like a additional pi-shaped bond on the top of the sigma bond. Those are more available to make new bonds because of that. Okay, makes sense, right? So then this is a much easier electron that you can use for making bond to something that is positive. So this electron, the double bond in this one, will behave like a nucleophile. Okay, so in this case, this hydrogen in the bromic acid here will behave like an electrophile. So same reason here. It attacks a hydrogen. Can you guys guess why? That will attack the hydrogen, not bromine here. If you look at the periodic table, bromine should be the one that takes the electron, because the hydrogen is up there, bromine is somewhere on the right. So when it happens, this one, hydrogen is also small too. If you think about the bromine, is really big, right? So this is an easier target for the alkene to attack. Okay, so then what happened to this one here? There's the shared electron here goes on here. Okay. So do you see my arrow here? It's four-headed. Means what? I'm showing there's one bond, there's one pair of electron, right? So if I do this one, means not one, but two electrons moving to bromine now, breaking this bond right there. Makes sense, right? Okay. So if I redraw this one over here, I'll draw the four-headed arrow to hydrogen. Okay, and a four-headed arrow on the top of the bromine. This is very kind of somewhat sequential. There's a stepwise, but you can say kind of moving this way. So you'll see this in also transition state, direction intermediate. But anyway, makes sense, right? So this is how you can do it. So eventually, what it does is now you don't have a double bond, right? You don't have a double bond because you use the one having the p orbital, pi electrons are moved to bound to the hydrogen here. So now you have this is this one, okay? This is all previous hydrogen over here. This is newly bound to this carbon here. And if you look at this one over here, has a 1, 2, 3 electron. But as you know, carbon is group 4, so it will be positively charged. Because it only has 3. So the carbon should have a 4 valence electron around it, but it only has 4. Only has 3. One has this reaction here. So they have only 3 available valence electron under this carbon. So this carbon becomes positively charged. We call this carbocation. It's like a carbon and cation, so carbocation. Okay. And then, so when it happens here, the next part is you have bromine is negatively charged. So if you look at over here, it has a 1, 2, 3, 4, 5, 6, 7. But now it has 2 is on here, so it'll be 8. Okay. So you have 1, 2, 3, 4 lone pairs. So, but this is group 7, but it has 8 because each lone pair has 2 electrons. So it becomes 1 negative charge. Okay, makes sense, right? So now in this case, this will behave like a electrophile too. Sorry, liquefied. Then they're going to make, so you see it's a four-headed arrow too, okay, over there, and they bond to this carbocation here. Okay? This will look for something that is positive, so it's a nucleophile. So this will now, at this time, this will behave like a liqueophile. And this will be something that also bonding to something negative, so it will be carbocation is also kind of work as a electrophile as well here. Okay? So then outcome will be this. It's a bromination. Okay? So you put the bromine on the alkene compound. So you have a bromoethane. Makes sense, right? So this will be a good example of addition. So you add it on. You add hydrogen and bromine on this alkene compound become alkane with the bromoalkene, bromoethane, ethane. Makes sense, right? Good. Okay. So the let me actually. All right. So don't worry about this one too much. We'll do this together. Let's do some practice. So if I give you cycloalkene like this, okay, and then I'll do the same. Can you guys do this one real quick? Maybe I'll give you 1 or 2 minutes. Okay, about 1 minute. We'll do this together. But I kind of want you to try it first. I know it's kind of take some time when you try it for the first time, but you get used to it. I promise. Okay, about 30 seconds. We'll do this together. Um, okay, so you got this one right? Okay, you good? So there's one more thing I want to mention is you may do this one. That's okay. But if you look at if it's a multiple choice in the exam, I don't normally show the hydrogen because it's hydrogen always implied in the structure. You guys remember this, right? So even though I didn't show you, I mean there's a hydrogen here, hydrogen here, hydrogen here, hydrogen here. We all know this, we just don't show it. So what I didn't do was there's also hydrogen here. There's one, this is double bond, but there's two for each. I just implied them here and over there. So even though you don't see the hydrogen here, just Roman is just good enough, or you can find it on the multiple choice. Okay. Sounds good, right? So another thing I want you to know is this one. Whenever you do this, I might also ask you, where is a nucleophile, where is your electrophile? Okay, so in that case, you need to circle this part to be a nucleophile. And you need to circle this part, or we can say this one is okay, because this is a part of the compound, that's okay. But more specifically here, right? So you can say this is where it work as a what? Electrophile. Okay, it's a nucleophile. So this might be also the exam, the question you may see on the exam. So I'll give you some not maybe full equation, just these two, and then you can choose where is the nucleophile, where is the electrophile, and you can say, oh, this is a nucleophile because it will attack something that is positive, which is hydrogen, because it's a lot of electron are kind of attracted to the bromine already, but it's very exposing to their nucleus, which is positive. So the not free, but most available pi electrons and the p orbital in this double bond will attack there. So it's a nucleophile, electrophile, all that. Okay. Let's do one more. Okay. There's a okay. So this is a very similar one. Over here, okay? So maybe we can today this maybe 1 or 2 minutes. This is one more thing. This is what we call, we're gonna talk about this in the maybe next time as well, maybe a month later or so. This is now 1, 2, 3, 4, 5, right? Instead of 4. So this is carbanium. So it's like a carbon anion. It's a carbanium. So it's negatively charged. But probably on the exam, I wouldn't put the charge because you should know by just counting the electron there. So just remember, I might not give you the formal charge sign, but you should know by just counting the electron. If there's a lone pair in the carbon, 3 single bonds, you mean 1, 2, 3, 4, 5 instead of 4. So it's a negative charge. You should know by the time you're gonna take the exam too. Okay? So carbanium here, and just yeah. This is a bit harder, I think, but very similar mechanism we did before. So maybe 2 minutes. Okay, 1 minute. So here's the thing. If you see something looks like this is a very electron like a reach because it has a carbanium is a negative charge, a lot of electron density is here. But if you think about this one, if you draw this more detail, this is what it looks like, right? This is actually what it looks like. But like I said, because of this bromine here, which is big, and also kind of drawing the electron here, so it's actually kind of taking the electron to the bromine much more. So the carbon, because of the neighboring bromine, will be, relatively speaking, electron poorer region. So this will be easy to detect this nucleophile. So this will behave like a this will behave like a nucleophile, and this can be it's an electrophile because it's now it's electron very poor because of the bromine. Okay, it's not double bond, it's the bromine. Okay, so that's why they can attack here. So then this bond here goes to bromine because bromine is taking the stronger force to taking this electron. So it becomes negatively charged, and this is bound to here, which is same as what? Which is the same as, so this is the answer, right? So this is the same as this one, okay? So just remember on your exam, I'll imply all the hydrogen, because we all do. Organic chemists all don't show the hydrogen unless it's important to show. Like some reaction, you may need to present the hydrogen so you can explain the reaction more easily. But normally, it's just this, okay? But you know there's the 3 hydrogen, 2, 3. You know that, right? Because we did it, okay. The 1, 2, okay. So this will be your answer. That is the job we need to do. All right, let's do a couple more. We have ammonia and chlorine. Okay. Yes. This is a bit tricky. Now see, yeah, but you can try. So 2 minutes again. Yeah, this is a bit tricky, I see. This is I'll just show you. So this is a bit tricky. This one, what happened to this one is here and here. This is sort of kind of you'll see a lot because of this nitrogen. Nitrogen with the lone pair is very good electron donating groups, like amine groups with the lone pair. That's why this will behave like a nucleophile, like donating the electron to something else. So it's very electron like a high density, and this is become very good electron donating groups. It's very common in organic chemistry. So that's why either choose, because they're pretty same in the electron activity, just choose any one of them. And those one goes to the other one, which is also quite electronegative anyway. So this is what become like. Am I right? Right? So here's the thing. So the nitrogen is group 5, right? 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4. Okay. So this is a tricky one, I see. But this one is just the nitrogen. And with the lone pair, the mean groups Y type of structure, they're really good electron donating groups. So I'll show you this maybe more times in the later chapters. But this is because of the lone pair on the nitrogen, which is also quite electronegative elements. Okay. All right, so just do one more and we'll move on. I think just one more. Okay. I think you guys by now getting some idea now, right? So if you just do, oh, there is something negative, and now there is a bromine, and which electron will be attacked to, which bromine is too large, and quite high in the polarizability. So maybe also neighboring carbon. Because of that, will Okay, about 1 minute. Here's, so just make sure whenever you do this one, use a full-headed arrow. You know by now, right? It's polar reaction because it shows very clear nucleophile and electrophile. Okay, so if you do this together, right? The lone pair goes there, okay? Goes there, okay? So you're going to have some ether groups here with the bromine and I, okay? See, yeah. So this is the, okay? So in here, which one is a nucleophile? Right? Okay. And then this is will behave like electrophile. This carbon because of the bromine or the neighboring atoms. Make sense, right? Okay, I'll move on. So we'll yeah. The next part we're gonna talk about the Born energy, chemical bond energy. So as you know, you guys are you guys taking also bio, right? Biology class. So you're gonna learn about this on your bio classes as well. But eventually, in all living organism use their potential energy to make them living, the sustainable energy, daily life. Because of the, we have a lot of energy are stored inside the chemical bonds. So we're gonna talk about this in this chapter. We only have 5 minutes, but let me try to start reviewing from the Jenkins 1 and 2. So do you guys know? So before we get to the Born energy, we need to get those 3 concepts first. Well, these 2 is enough, but we'll get to 3. It's just the reviewing Jenkins 1. So you guys know what this is, right? This is a change in Gibbs free energy. You guys remember this, right? Is this a good reminder, right? The Gibbs free energy. Do you guys remember this? This is delta H. So delta means a change in something. So delta means change in something. Then H means it's a change in enthalpy. Okay, change in enthalpy. Okay, and then this is a change in entropy. Okay, entropy. You guys may heard entropy many times anyway, but this is entropy. So there are a couple of things I want you to remember before I move on to the next part of the chapter 6. That is, there's a change in Gibbs free energy. So if that is the negative, it's a spontaneous reactions. Okay. If it's a positive, so this one rise. If it's positive, it's non-spontaneous. Okay. So it's simply because of the tendency of the compound or the atom that wants to be always located in the lower energy status. Because whenever they locate in the lower energy status, they can be more stabilized. So I probably told you in the beginning of this semester, whenever they're in the low energy state means they're stable because they don't. Here's one thing. What do you mean by stable? First of all, what do you mean by stable? Well, what do you mean stability of the compound? So stability compound is it's very simple in chemistry. It's not like other factors or anything. It's just simply how much kinetic energy it has. So if it's very high in kinetic energy, means it's very unstable. And also, when they're very high in kinetic energy, what happens to the molecule? You're gonna actually learn this in over 2, maybe next semester or some other classes. Whenever they're very high in energy, they actually move really, really quickly and vigorously. Meaning, if you look at the atom here, this also chalk, also made of something elements for sure, but it looks just stand still in the macro scale wise, but in the very atomic or molecular scale wise, it's very unstable. Only relatively term wise, meaning it's still moving within the structure right there. So if it's do less and less, that means they're kind of locating in a much lower and lower energy because they don't have much energy to move or in the kinetic energy form in any way. So they're less moving, less vigorously vibrating, meaning it's more stable. So that means they're in a very low energy states. Makes sense, right? Because if you're very high in energy, what you want to do is exercise because you're full of energy, just move a lot of exercise. But when you're done with a lot of exercise, you're exhausted, you're tired. So you don't want to move at all, or just a little. That's the same for the atoms or molecule. So that's why they're very low in energy, then they can be very stable. So then if that is negative, meaning your product will be in a much lower energy status after reactions. So this is why they want to do it voluntarily. This becomes spontaneous. Because everything wants to be in the low energy status, but that reaction makes that happen. The molecule says, oh, let me go for it because I want to be more stabilized. So when it's negative, that means it's spontaneous. So negative means it's energy from the products to so this is the reactants, this is the product. So when they go huddle, which is we call this activation energy, we're going to talk probably on Friday. But when they go from the huddle, they're going to be more stabilized in the P. So in that case, they want to be do it voluntarily. So you don't have to do anything, and at some normal condition, this will be just automatically happening. Okay? But if it's positive, it ends up in some higher position, which they don't want to do it. Well, I wouldn't want to be more unstable, right? I want to be stable, but if that reaction makes me more unstable, I don't want to do it. So we'll not do it voluntarily. We need to force them by putting a lot of energy into it. So then we name this non-spontaneous. For themselves, it won't happen because of it, okay? So this is something I want you to remember before we probably move on to Friday. So I'll quick. So the entropy is a degree of disorder. So if it's moving much faster and very high in kinetic, they move faster and longer, right? Then it's very high in entropy. So the outcome or the reaction makes it more unstable. It means it will be the change in the entropy will be plus because the product will be more energetic, more kinetically active. So this is positive. If it's the other way, it's more stable, it's more calm, then the change in entropy will be lower, right? So it'll be negative. Okay. So then the entropy-wise, okay, entropy-wise, this is about your heat energy flow, or just heat. Okay. So if heat is going out from the system, which is your reaction? The reaction. This is an exothermic reaction because it's getting out. It's exothermic reaction. If it's going in, so energy going from, so this is the system, everything else except the system is the surroundings. If it's going in, it's endothermic reaction because it's going in. It's like an endothermic reaction. You guys remember this? Endothermic reaction? Okay. So exothermic, endothermic reactions. So this one. Well, I'm sorry. I don't have time. I'll do this again on Friday, once more. So, but this is something we need to know for the next part of the chapter 6. Okay? So let's do have extra credit.